Hi, I am Hossein Rafipour, and in this video I'm going to briefly introduce Bench, that is a new FSL tool that uses a Bayesian framework for identifying parameter changes in biophysical models. A central challenge in neuroimaging is linking what we see on the scan to the underlying biology. For instance, in the case of white matter hyperintensities, the key question is which microstructural change can explain the contrast compared to a normal tissue. To address these kind of questions, we typically acquire data that is sensitive to the change of interest, in this case, diffusion MRI. We then use a biophysical model to translate these signals into meaningful parameters and finally compare those parameters across groups using a model-based approach. A common example of these models is the diffusion tensor model, which you have already seen in the earlier course material. By fitting the tensor model in both controls and the patient group, we can derive measurements such as fractional anisotropy and mean diffusivity for each group. In this case, we observe that FA is increased while MD is decreased in the patient group compared to the control one. This provides a valid comparison, but it raises another question. What do such changes in FA and MD actually tell us about the underlying tissue? The difficulty with interpreting measures such as FA and MD is that brain tissue is far more complex than what a simple diffusion tensor model can capture. Water diffuses in several distinct environments within a voxel, each with its own diffusion properties and signal characteristics. At the most basic level, we can distinguish between the intracellular or axonal space, the extracellular space close to the axons, and the water that is away from the axon boundaries and can diffuse freely. There are several multi-compartment models in the literature that can explain these kind of data. An example of such models is the so-called standard model for diffusion in the white matter. It describes three compartments: free water, which is modeled as a Gaussian diffusion or a ball; interaxonal water, represented as sticks where diffusion is restricted to a single direction; and extraaxonal water, which is modeled as zeppelins, that is Gaussian diffusions elongated along a preferred direction. This model has 8 free parameters, including the signal fractions of each compartment, the diffusivities that reflect how quickly water diffuses within each environment, and the dispersion index that captures how coherent or dispersed the fiber orientations are. However, diffusion data alone cannot constrain all of these parameters. To make the model tractable, we typically impose additional assumptions. The most common practice is to fix some parameters to predefined values and estimate the only remaining parameters. For example, the widely used NUDI model fixes the diffusivities and focuses on estimating the signal fractions and dispersions. To assess microstructural changes in white matter hyperintensities with NUDI, we analyzed 3,000 subjects from the UK Biobank dataset. For each subject, Bianca was used to identify voxels with white matter hyperintensities and normal tissue. We then estimated NUDI parameters in each voxel and each subject using a nonlinear optimization approach. Finally, we applied a general linear model to compare voxels with and without white matter hyperintensities to measure the NUDI parameter differences between groups. These maps show the estimated z-statistics for changes in each parameter for a subset of voxels where there was at least 10 subjects with white matter hyperintensities. In this analysis, we fixed the interaxonal diffusion coefficients to 1.7 in every voxel across all subjects. With this assumption, white matter hyperintensities show an increase in free water in most voxels and decrease in the interaxonal to extraaxonal water ratio. A similar trend is observed for ODI, though less consistently across voxels. We then repeated the same analysis, but with a different diffusion coefficient fixed at 2.5, as suggested by more recent studies. This change in the fixed value reverses the earlier findings. Now, free water fractions decrease and ODI shifts toward more positive changes. The key message here is that these results are highly sensitive to the choice of fixed parameter values, and crucially, these values may also change themselves across voxels and subjects. So, The strategy of estimating some parameters while fixing the others has two main problems. First, it ignores the possibility that the fixed parameters themselves may explain the observed contrast. But, more importantly, even if we ignore those changes, if the chosen fixed values are wrong, this can completely distort the inferred change in other parameters. For instance, fixing diffusivities to a wrong value as showed earlier can change our inference for signal fractions. So this sensitivity is a major limitation of the conventional approach if the models are big. The central idea in Bench is to try to identify the parameters that has changed without relying on parameter fixing or full model fitting. In Bench, the goal is not to estimate parameter values directly, but rather to determine how likely it is that a change in each parameter explains the observed contrast in the data. These maps here show the main output of Bench, the probability that changes in individual parameters account for the differences seen in the white matter hyperdensities compared to normal tissue. The brighter the map means that the probability for changing that parameter is higher. Most importantly, in this case, every parameter in the full model is considered to be able to change without fixing any of them, with the cost that no single parameter value is explicitly estimated from the data. Now, let's briefly look how Bench actually works. To make the concepts clearer, we use a simple TOE example instead of the complex diffusion data. Consider a forward model, like a quadratic in this case, with three free parameters, A, B, and C. Given a set of data points, one could invert this model and estimate these parameters by maximizing a likelihood function, or equivalently by minimizing some error function, using nonlinear optimizations. In this case, ideally without any noise, only 3 data points would be enough to estimate these 3 parameters. Now, suppose we have 2 data sets representing 2 experimental conditions, for instance, red for control and blue for patients. If we want to estimate parameter changes, the conventional approach is to fit the model separately to each of these data sets and then compare the fitted values across them. For instance, in this case, the results of fitting for each data set suggest that parameter B is the parameter that is changed across the 2 groups and can explain the difference that we see between these 2 data sets. This approach works very well when the model is small and the data is sufficient to constrain all the parameters of the model. However, if the measurements are limited, for example, with only 2 measurements and 3 parameters in this case, the parameter estimation becomes an ill-posed problem. In other words, there are infinite many parameter combinations that can explain the data equally well in each group, with no single solution preferred to the others. This problem is also known as model degeneracy. In such cases, the conventional approach is to add extra assumptions to make parameter estimation feasible. For example, we might assume that the parameter A is fixed to a specific value, 0 for instance, to reduce the model to a simple linear form in both groups. However, while this makes the estimation possible, as you can see in this case, it can also introduce significant biases and potentially lead to misleading interpretations for parameters B and C. This is exactly the strategy that is used in NUDI when we fix diffusivities to some values and estimate signal fractions. In Bench, we use a different approach. Instead of fixing parameters, we make a different assumption, that is, the change is sparse. For instance, only one parameter can be different between the 2 data sets and the rest are the same. So let's focus on the first plot. If only parameter A changes while B and C remain the same, this plot shows how the measurements would be affected. Here the red curve shows the baseline and the gray area shows the effect of changing A up to 1 unit. We see that this predicted change does not match to the observed data in blue. If instead we assume that the parameter B is the only parameter that is changed between the 2 groups, the model predicts a decrease in the first measurement while an increase in the second one. which is consistent with the observed change in the blue one. Finally, if only parameter C has changed, both measurements should increase with the same amount, which again does not match with the contrast. So in this case, only a change in parameter B can account for the observed differences between red and blue. To illustrate this idea in a more clear way, we can replot the same data in a slightly different plot, as a scatter plot in this case, where x-axis is the first measurement on the left and y-axis is the second measurement on the right of each plot. Now, each dataset is shown as a point in this scatter plot. The arrows here now show the expected direction of change in the measurements when we change each of these parameters. For instance, if the parameter C has changed in the baseline, we expect that both measurements should increase together with the same rate. Instead, if parameter A changes, we again expect both of the measurements increase, but the rate of the increase is different for each of the measurements. And if parameter B is the changed one, we expect that the first measurement on the x-axis decreases while the second measurement would increase. So the observed data in this case exactly falls along the direction that is shown by the change in parameter B. So we can expect that the parameter B is the one that can explain the contrast between these two data sets. In short, if we can estimate these arrows per parameter, then we can compare them with the actual contrast in the data, and based on that determine which parameter can explain the observed data and which does not. So each arrow represents how the measurements would change if the corresponding parameter changed. That is technically the derivative of the measurement with respect to that parameter. So by estimating these derivatives from the data, we can predict the expected direction of change. We do this by training machine learning models that can estimate the derivatives given measurements. So we take some measurements as input, and we then try to estimate the derivative with respect to each parameter. And once we have that, we can tell how the data would change if that parameter has changed. Briefly, this schematic shows the full bench pipeline. There are two phases. In the training phase, we generate many pairs of measurements and the derivatives by sampling the parameters from a prior distribution and passing them through the forward model. We then use these samples to train machine learning models that can estimate the derivatives with respect to each parameter given the measurements. This procedure is repeated once for each parameter and does not require any real data. In the inference phase, given observed measurements and the contrast, we use the trained models to estimate the derivative with respect to each parameter from the baselines and then compute the probability that each parameter can explain the contrast. In the next few slides, I will demonstrate how Bench performs on simulated data as a validation step and compare its results with those obtained from conventional model fitting approach. For these validation experiments, we used full forward model of diffusion that was introduced earlier. We trained models of change for each of the 8 pre-parameters of the model. We then generated simulated dataset pairs, where in each pair, only one parameter was different between the two groups. The trained models were evaluated on these datasets to test whether they could correctly identify the changed parameter. For comparison, we also applied the conventional approach by fitting the model to each dataset separately and then try to infer the changed parameter from the estimations. In the first experiment, we validate Bench on a model with 4 free parameters. That is the simpler version. The two confusion matrices here compare the conventional fitting approach with Bench. Each row shows the true parameter that was changed in the simulation, and each column shows the parameter that was identified by the method. A perfect result would be a diagonal matrix, meaning that all the parameters identified correctly. In this small model, Both methods perform well, and confusion matrices are nearly diagonal in both cases, showing that either approach can reliably identify the change when the model is simple and well constrained. We then repeated the same analysis, but this time using the full model where all 8 free parameters can change. This confusion matrix shows the bench results. Bench could reliably detect changes in signal fraction parameters and fiber dispersion, though there was some confusion for diffusivities. We then tried to do the same analysis but with the conventional approach. In this case, since the model is degenerate with so many free parameters, it is not possible to estimate any parameters with a reasonable variance, so no change could be detected reliably. The key message here is that when the model is big and we don't want to fix the parameters, then it's not possible to identify any change. But with bench, we can identify change in most of the parameters and also understand which parameters could be confused with the others. Now, let us return to the original example problem. That was detecting macrostructural changes in the case of white matter hyperintensities that we see in T2 FLARE images using diffusion MRI data. Let's see, in terms of the parameters of the standard model of the white matter, which parameter can explain this observed contrast. Similar to the earlier NODI analysis, we used the data from the same 3,000 subjects from the UK Biobank dataset who showed white matter hyperintensities at some parts of their brain. Bianca was used to identify white matter hyperintensity voxels and normal tissue. At each voxel, we splitted subjects into those with and without white matter hyperintensities and calculated the baseline from normal tissue and the contrast as the difference between hyperintensity and normal tissue, and also estimated the uncertainty in the measurements. Finally, we applied the train change models from the simulations to estimate the probability of change for each parameter. Each map in this plot shows the probability that a change in that parameter can explain the observed contrast in white matter hyperintensities compared to the normal tissue for a sample axial slice. Brighter voxels indicate a higher probability of change in that parameter. The maps are normalized so that the probability across parameters sum to 1 per voxel. In this example, changes in extra-axonal signal fraction show the higher probability in many of the voxels, while most other parameter maps remain flat, meaning that they are not explaining the contrast well. To summarize the maps, here I show the model with the highest probability color-coded. In the majority of the cases, a change in the extra-axonal water can best explain the observed change in the data. This is actually in line with the only change that was consistently detected using the restricted NODI model. This is with the advantage that here we have not fixed any of the parameters and they could vary across the groups as well. Bench is implemented as an FSL command line tool. The inference is straightforward. You call bench followed by one of its subcommands, such as train, summary, GLM, or inference. To run bench, 3 main inputs are needed: preprocessed diffusion data, warp builds to bring diffusion into a standard space, and the design matrix defining the contrast you want to test. With these in place, the pipeline can be executed directly from the command line. The first step is training. This is done with the subcommand bench train. You specify the forward model, for example, the standard model that is implemented in the library, then provide the corresponding acquisition parameters such as b-values, and then set the name for the output, where the train change model will be stored with all its weights. This step only needs to be run once for each forward model and acquisition scheme, and the resulting trained model can be reused in later analysis. Training change models may take up to a few hours depending on the number of samples for training and the model. Running bench directly on the raw diffusion signals has 2 main problems. The data is high-dimensional and strongly correlated, and they are sensitive to fiber orientation, which is not directly relevant to the macrostructure. To overcome this, we extract summary measurements that are orientational invariant and capture the diffusion signal in a lower dimensional space. For this, there are two options available in Bench. It can be either based on diffusion tensor model or spherical harmonics. Bench summary subcommand takes the diffusion data as input per subject and then produces summary measurements such as mean diffusivity and fractional anisotropy, and then transforms these measurements into a common space using the warp fields. Once we have the summary measurements per subject in a common space, the next step is running the GLM. This means we need to estimate three things per voxel: the baseline signal, the group difference or contrast, and the noise covariance. These quantities are then passed to the inference stage of the bench as the final step. To run this, we use the subcommand bench GLM, where we provide the design matrix and contrast, the subject list, and the directory of summary measurements. The output would include maps of the baseline measurements, the maps of the contrast, and the noise covariance. Finally, in the inference stage, we take the change model trained from the simulation step and the output of the GLM to estimate the probability of change in each parameter. This is done with the subcommand bench inference. The results include probability maps for each parameter that shows how likely is that a change in that parameter can explain the contrast we estimated from GLM step, and also a no change probability map that shows how much no parameter change and only noise can explain the difference between two groups. This also includes the estimated amount of change per parameter. These are the main output of Bench, and they can be visualized using FSLIs. Bench also comes with an FSLIs plugin, which is included in the source directory. This can be installed following the standard FSLIs plugin installations instructions. Once installed, it allows you to load the Bench output directory in FSLIs and then look at your results. On the left, you can see the voxel-wise map of the inferred change overlaid on the structural image. On the right, the plugin shows the probability of change for each parameter, together with the estimated amount of change. In this voxel, for instance, the analysis points to the extra-axonal signal fraction as the most likely parameter explaining the observed difference, with corresponding decrease in the extra-axonal fraction. So far, Bench was explained and used in the context of diffusion MRI data analysis, but it is a general framework for detecting parameter changes without the need for full model fitting or fixing parameters. It can be applied to any forward model and dataset, and it is particularly useful when the model is over-parameterized and the data cannot constrain all the parameters. It is not limited to the group contrast and also can extend to regression analysis where there are continuous explanatory variables. To run Bench, the users need to provide a forward model, prior on the baseline parameters, and a way to define summary measurements that represent data in lower dimensional space. To finish, here are some more resources if you would like to explore Bench further. On the left is our neuroimage paper where we first introduced the method and it has all the details. And on the right, there is a more recent application paper on imaging neuroscience that tries to link macroscopy to diffusion MRI using Bench on extended biophysical models. The Bench code is openly available on GitLab, and you can also find the step-by-step practical as a part of the FSL course material. Together, these resources provide both theoretical background and hands-on guidance for applying Bench to your own data. Thank you for your attention.